Hello everyone and welcome back to Solid State Physics in a Nutshell, brought to you by the Physics Department at the Colorado School of Mines. My name's Eric.
And I'm Nicole.
So far we've been talking about vibrational modes and how they're distributed, but we haven't really talked about how they're filled. Today we're going to be using some statistics to talk about the Planck distribution and the heat capacity for phonons.
As a reminder for those who haven't had Gen Chem in a while, heat capacity is defined as the energy required to change some body by some delta T. And what we define as a body may seem ambiguous, but it could be anything from a mole to a gram to a centimeter cubed of a material.
Also recall from the ideal gas model, heat capacity is 3 kb over 2 per atom, where kb is our Boltzmann's constant. Experimentally, room temperature solids were found to exhibit 3 kb per atom, which became known as the law of Dulong and Petit. However, this model totally failed at low temperature.
But then at the turn of the 20th century, here comes Einstein and postulates the simplest model for a solid, where each atom is an isolated harmonic oscillator and all the atoms are oscillating at the same frequency.
So this is a really dumbed down model compared to the dispersion we've been using. Instead of a broad range of phonon frequencies, we only have one frequency. Now, all we need to add is a dash to statistics to see how this mode is filled. Let's start with the energy of a particular mode as U sub n. Total energy of the system is then 3n times the expectation value of n h bar omega.
I know n is the number of cells in the solid, but what's this 3 doing here? And what happened to the 1/2 term?
The 3 indicates our solid has vibrational modes in 3 dimensions. We also drop the 0 point energy term because later when we take the derivatives, it'll drop out on its own.
And the expectation value of n is the population distribution, right?
Exactly. Because we said phonons act like bosons, we're going to use the Planck distribution to describe how these modes are filled as a function of temperature. Plug this back in, and now we have an expression for the total energy in our quote-unquote Einstein solid.
Well, that seemed awfully easy. Let's see how our heat capacity looks. All we have to do is take the derivative of U with respect to temperature, and we end up getting something of the following form. To make it look a little nicer, let's define this variable x that is inversely related to T and rewrite our heat capacity as so.
Before we plot this mess of a function, it'd be a good idea to talk about the high and low T limits and see what we can learn from them. Why don't you start with the high temperature limit?
At high T, x will start to approach 0. Taking the limit of C, we end up getting 3n kb. Hey, that's the law of Dulong Petit. So far we've got an agreement with experiment, so that's a good sign.
When we look at low temperatures, our heat capacity has an exponential dependence on T. In practice, we see actually a T cubed dependence experimentally. So while we're getting a reduced heat capacity, like we generally expect, the temperature dependence is wrong. And next time we'll go look into the nitty-gritty of why this is wrong.
So I guess I'm confused why we get different temperature dependences at the different limits. In a harmonic system, the energy spacing is always constant. So why isn't heat capacity just constant with temperature?
You're right about the energy spacing, but it's the population of modes that changes with temperature, and that's what affects the energy of the system. To really see this, I'll plot n versus t for a frequency of, say, 10 terahertz.
So the change in phonon population at the high temperature region is linear, but sublinear at low temperature.
Right, and since n is the only thing that changes with temperature in our energy equation, its temperature dependence is reflected in the heat capacity. Okay, so that's about all we want to cover today.
As a recap, today we introduced the Planck distribution, which describes the population of phonons as a function of temperature. We then applied Einstein's model of isolated oscillators to the heat capacity of phonons, and obtained pretty good agreement with experiment at high temperatures.
Although Einstein's model didn't get the low temperature behavior quite right, you at home should consider why he did get it right for the high temperature limit.
So that's a wrap for today. Next time, we'll introduce the Debye model for phonon heat capacity. Thanks for watching Solid State Physics in a Nutshell. See you then.